Okay, empirical formulas or empirical formulae, or however you like to say it. That's what we're doing now. All right, now you guys just did one, but I'm going to start with what Salman Khan does and just do some examples. And I want to do them in kind of a systematic way, a four-step method that you can use to do these. Starting with percentage, so going from what's called percent composition to the so-called empirical, or also known as the simplest formula, meaning the smallest ratios of the subscripts or of the moles. So formula, percent composition. Of course, first of all, we should take a look at what we mean by percent composition. If we have NaCl, for example, if we had 1 mole, so if we had 1 mole of NaCl, that means we have 22.99 grams of sodium and 35.45 grams of Cl. So the percent sodium would simply be 22.99 over the total here, 22.99 plus 35.45 times 100%. That's going to be 22.99 divided by the sum of 22.99, 35.45. This is 39.34%. And now we could get, in this case, we can get the percent chlorine just by difference. We know that the total is 100. They both add up to 100%. So we'll just take 100 and subtract 39.34. And we get 60.66%. So that's what we mean by percent composition. But what we're talking about here is going backwards. So we're talking about going, see here I gave you the formula. And then we found the percentages from that. But going backwards is a little bit different. So we're going to start with percent composition, and we're going to go to the empirical formula. And the first step, so 4 steps that we want to try here, or that we want to use. The first step is percent to mass. So we want to change those percentages to a mass. The second step is going to be mass to mole. And you guys just did this step in the tin iodide lab. You went from the mass of the tin and iodine to the moles. And then 3, you did this step as well, divide by smallest. And then the last step, you probably found that you didn't have to do in this lab, and that was multiply to whole. Multiply to whole, meaning whole numbers. So that's if you end up with something like a fraction after you do step 3, or 1.5, or 1.33, or 1.67, or 0.67, or whatever you're going to, well, it won't be 0.67, but you're going to multiply that through by something to get a whole number. So let's look at step 1, and we're going to do an example here. In this example, we've got a compound that is 36.5% sodium, 38.1% oxygen, and 25.4% sulfur. Now, the reason this is called an empirical formula, empirical just means experimental. This is based on experimental analysis, just like you just did. So you could do an experiment similar to what you just did, and you get some data. And then from that data, from that empirical experimental data, you find the formula. So this is called an empirical formula. So the first step is to just convert these to masses. Well, we want to convert this to a mass. The easiest way is assume that we have 100 grams of the compound. It doesn't matter how much we have. Remember, percentage is the same no matter how much of the compound you have. So whether I have a gram of the compound or 5 grams or 500,000 grams, it's going to be the same percentage of the elements. Constant proportion. So if I assume 100 grams, that just makes it easy to convert this to grams. That means I have 36.5 grams of sodium. And that means that 38.1% of oxygen turns into 38.1 grams oxygen. And 25.4% sulfur turns into 25.4 grams of sulfur. Now step 2, I'm going to convert each of these to moles. So this is going to be 22.99 grams, 1 mole, 16.00 grams. Getting these numbers from where? 22.99, 16.00, where are they coming from? Periodic table, right. Those are moles. So 1 mole, remember, just slap a G on the end of any average atomic mass and you get a mole. And sulfur is 32.07. All right. Now, so if I do these calculations now, I got 36.5 divided by 22.99 gives me 1.588, and the units there are going to be moles of sodium. And then 38.1 divided by 16, 2.381, and that's moles of oxygen. And then 25.4 divided by 32.07, and that is 0.7920 moles sulfur. That's step 2, mass to mole. Mass to mole, and that's step 2, it's all done. So you did this step. Now the next step, step 3, is when we're going to divide the higher ones by the smallest. Divide them all by the smallest number. And this is just a technique. So step 3 is just a technique for converting them to ratios, essentially. Basically what we're doing is, in step 3, we're asking this question. If the smallest component, or the least component, of the compound had a subscript of 1, what would the others be? What would the others be? And so that's why we divide them all by the smallest. You're basically saying, you're going to say how many moles of sodium do we have per unit of sulfur, and how many moles of oxygen per unit of sulfur. What would the others be? So I'm going to take 1.588 moles of sodium. I'm going to divide by 0.7920 moles sulfur. 1.588 divided by 0.792 gives me 2.005. That looks nice. And that is moles of sodium per mole of sulfur. I'm going to do the same thing with oxygen. 2.381 moles O over 0.7920 moles sulfur. .006. Now again, I'm going to be rounding this, right? So clearly I want to round the first one to 2 and the second one to 3. In other words, I don't want to say that it's a 1000 to 2005 to 3006 ratio. See what I'm saying? This is mole oxygen to mole sulfur. So I could write kind of a, just take a first stab at it here. I've got Na, O, and S. And S is the smallest, so I'm saying if S were 1, what would the others be? And I'm going to write 2, and 3. Now that makes sense. Those are small numbers, small whole numbers, and I didn't have too much error here, just 5 thousandths here and 6 thousandths here. Notice that I did not write, as I said. I understand the concept of experimental error, and I expect it. And so I'm not going to assume that this is a precise, exact number and write 2005, 3006, 1000. In fact, I actually rounded that number right there. So you are not going to write something crazy like that. We want small whole number ratios. Now, I'm not done yet, because in this case, what does this tell you? Sodium tells you something. It tells you this is a blank compound. This is an blank compound. Ionic compound, right? So because it's ionic, I'm still going to write the sodium first, but what am I going to do with the O3S? What do you think? This is ionic. Does it remind you of anything? Sulfite, perhaps? SO3? So in some cases, I'm not going to hold you to the order of the elements. Like if this were a covalently bonded compound, I may not take off points if you got the order in which you wrote them wrong. But in this case, I would, because you should recognize that as ionic and realize that one S and 3 O's are sulfite. Okay? And if you want, take a look at your table of polyatomic ions. You can verify that. All right, so that's how we do this. Now, notice we didn't need step 4. So what I want to do next is I want to do a problem where we need step 4. Needing step 4 requires a different example. So here's our second example. And in this example, we have a compound that is 36.2% aluminum and 63.8% sulfur. So we're going to do a different example, and this one's going to require us to go to step 4, which is multiply to whole. So first of all, we just change this right into grams. Make sure you understand why we're doing that, why we can say 36.2 grams. It's because we are, again, assuming 100 grams. 63.8 grams of sulfur. Now we convert to moles. And aluminum is 26.98 grams. Am I going too fast? I know it's good for you to try to do these along with me in your notebooks, because especially if you can try to stay ahead of me a little bit, that would be even better. It might be hard with me going so fast, but you will learn better if you do that. This is moles of aluminum. Whoops, 63 point. And then 63.8 divided by 32.07 gives me 1.989 moles of sulfur. Now, good time to mention this. Notice we're only on step 2 here. Do not stop here. You might be tempted to at this point. Because this thing looks a lot like 2, I might be tempted to write something like 1 to 2. Right? Do not ever stop at step 2. Always go to step 3. Capiche? So, step 3 is what? Divide by the smallest. So here I'm going to take 1.989 moles of sulfur. I'm going to divide by 1.342 moles aluminum. And I get 1.48. See, my mole ratio is not 2 to 1. 1.482. Now this is moles of sulfur to moles of aluminum. And in this case, I'm thinking, well, maybe I need to round that down to 1, but which is more likely, that I made an error of 50% or that I made an error of 2/100ths here, right? So, because it would make sense if this were 1.5, right? If that were 1.5, then I could go on to step 4 and I could multiply through. So, in other words, I've got AL1 S1.5. And if I multiply these through by 2, then I get AL2 S3, okay? And that's still a small whole number ratio. It's still something that's very common. Fe2O3, you see them a lot with the transition metals. Okay, so these are not uncommon ratios to find. Some other ratios that you want to look out for. Other ratios to look out for. This is 1.5. Something like this should ring some bells. Okay? 4/3. And now if you got 1 to 4/3, you could multiply through by 3, right? And then you'd change it all to whole numbers. What if you saw something like this? 5/3, again, multiplied through by 3, and you'd have a 3:5 ratio. So in a case like this, if you had 1 to 1.33, you multiply through by 3, and you get a 1:4 ratio. No, a 3:4 ratio, right? So these are not as common, but you might see these. Don't worry about things like this. All right. If I saw something like that, I wouldn't say, oh, that's, what is that? 0.1625. Eighth? I'm not going to do something like that. I'm going to, if I saw something like this, I would round down, okay? So don't worry about that. But a half, a third, 2/3, those are reasonable to multiply through. So questions on those? Let me give you one to try. Try this. Try this one. Let's see. 93.5% niobium and 6.50% oxobium. No.
Oh, I thought you were.
What is the empirical formula? I think it's NB, wherever it is.
It's the last one. Well, it's 41.
41, yep.
Good job, yo.